Hello, my name is Talha Hussein. I'm a member of Comet Aviation and Design Build Fly at UTD, and I'm going to be talking about initial sizing for your RC airplane. And I'll be making an RC airplane alongside with you. I'll be initial sizing it with you as I go. So there's two types of parameters I want to talk about, or will be using in this video. One's a decision. So sometimes you're gonna have to look at a chart and be like, I'm making a glider, and gliders typically have this parameter or this number. So you're going to go ahead and pick that number. If you're making it like a fighter jet type plane and you want it to be really maneuverable, then you're going to have to look at another parameter. And sometimes you have all the data you need, and all you need to do is just plug it into a formula, and it's going to spit a number back out at you. And this is going to make sense in a second. First, we're going to do wing sizing. That's what you always start with. So let's talk about wing cube loading. And this is our first decision parameter, right? Because what's going to happen is we're going to look at the chart on the right, and we're just going to pick a number. But first, let's talk about what is wing cube loading. So wing cube loading is a parameter that tells us how our aircraft is going to behave. How controllable is it for the pilot, right? So on the right side, we have, 0 to 17. So if it's 17, you're going to need a very skilled pilot, right? Wing cube loading is also directly tied to stall speed and your takeoff speed. Your takeoff speed, not as much, but definitely your stall speed. So you have a really high wing cube loading, it's going to be a lot easier for your aircraft to stall. It might have to go a lot slower, right? So, and on the left side, we have our formula, which is our weight over our wing area. It's in ounces, which kind of sucks. There's not a lot. The rest of our formulas are not going to be in ounces. So yeah, I did say I'm going to design a plane alongside with you. So let's go ahead and you know what? Let's also describe the type of plane I'm going to be designing. I'm going to design a glider type aircraft. I want really long wings, probably. We're going to talk about that a little more. But basically, I want an aircraft that doesn't have a lot of drag. It glides smoothly wherever it goes. So, what wing cube loading should I choose? I'm going to go with the wing cube loading of 10. Um, Not too high, not too low either. Let's see what they recommend. They say sailplanes. What do we have? Many, many trainers. 3D planes. I think I'm going to be making a 3D plane. I don't want it to be 2D. Uh, I think 10 is good, right? Um, I wouldn't go above 14 if you haven't designed an RC plane before, and I wouldn't go above 10 if it's your first time flying, if you plan to fly the aircraft yourself. So I'm going to choose 10 as my wing cube loading. And while we're still on this parameter, why don't I go ahead and decide a couple other things. I'm going to throw out a weight estimate, right? At this stage, when you're doing initial sizing, you might not know what your weight's going to be. So it's probably just best to give an estimate. I'm going to go 35 ounces. 35 ounces. All up weight. You want your all up weight because this counting batteries, counting your electronics, and the whole plane. So now we can kind of plug it into our formula. And this is where the other parameter I was talking about, your calculated parameter, which is the wing area here. So we have wing cube loading, we have the takeoff weight in ounces. We can go ahead and just calculate for the wing area. So let's go ahead and do that. Wing area. I'm going to write S because that is the variable that wing area is usually uh, written in. So we have wing cube loading here, and we have all up weight in ounces divided by my wing area. So I'm going to write S to the power of 1.5. I'm going to go ahead and solve for S. That gives us all up weight times wing cube loading. I'm going to have to move that exponent to the other side. All right. Now let's go ahead and plug in the numbers that we know. 30 ounces, 35, right? Times our wing cube loading, which I decided to be 10. Do this to it, and let's see what we get. I have a script, so I'm kind of cheating right now. But I did make the script on my own. I don't know if that makes it any better. Um, and I get a wing area of 0.19. Let's go ahead and round to 3. meters squared, or rather truncate. 0.193 meters squared. So this is my wing area based on my wing cube loading. I didn't really get to decide this because I decided that I was going to choose my wing cube loading and I knew my all up weight. What you could also do is, like, let's say, you know, you have your all up weight and you know what you want your wing area to be. You could go ahead and then check if your wing cube loading is valid. Of course, you can move these equations all around however you want. I'm just going to go about it this way. I think this is a good way to go about it. Usually, wing area is not a restriction you have to worry about. Maybe wingspan is a restriction you have to worry about, and many other things. Um, but there you are. Let's go ahead and continue. We've spent plenty of time on wing cube loading. So, aspect ratio. Aspect ratio, okay, to bluntly put it, it is the thickness of your wing over the length of your wing, right? Or maybe the other way around. Um, it's the length of your wing over your chord, right? So on the left, we have an aspect ratio of 33.5, right? And look at that, that's a glider, so that's what I'm going to be making, right? So it's really long and it's really thin wings. And on the right, we have a stubbier wing, if you will, right? An aspect ratio of 5.6. Now that what I said about aspect ratio, where it's the span over the chord, that's not entirely accurate because taper ratios come into the mix and things like that. The better way to think about it is actually the formula itself, which is b squared, right? Your wingspan squared over the area, right? So let's say you have a wingspan of 2 meters. So take 2 meters and then you square it, and how much ever your wing area fills up, that's your aspect ratio. That's also a stupid way of thinking about it, but like you get the idea. This is technically what your aspect ratio is. Now, why would you want a higher aspect ratio or a lower aspect ratio? So let's go look at a plane from above, right? So this has a really high aspect ratio. And let's say, assume these wing areas are the same. And there we go. Now, assuming these wing areas are the same, this has a smaller chord length, right? And we're going to be talking about this a lot more later. But what does this do for us? Whenever you have a smaller chord, your induced drag goes down. Your induced drag. Induced drag is a form of drag that I talked about in another video, and it primarily dominates at the lower speeds. So if you're making an aircraft, and for example, I'm making a glider, and a glider will probably stay at a lower speed, induced drag is definitely an issue for me. So I would want a high aspect ratio because that way my chord would be smaller along the span. And there's many other things to talk about, like taper ratios, your wing plan form. We'll go over that another time. Right now we're doing initial sizing, and aspect ratio is a parameter we have to pick. Why would you want a stubbier aspect ratio? For one, if you're making an aircraft that's a lot more maneuverable, that there's also really high loadings on your wing if it's that long, right? You can't turn really fast. There's a really big dihedral effect, meaning you're not going to roll crazily. So a lower aspect ratio is more maneuverable. Um, and obviously, if you're making a standard aircraft, pick something in the middle. Now, I'm going to go with an aspect ratio of 10. I think 10 is a nice high number. Let me go ahead and change that right there. Let's calculate for 10. All right. If I have an aspect ratio of 10, right, aspect ratio equals b squared over a, right, where a is wing area, so we should probably make that s, and b is wingspan, right? So I already know my aspect ratio because I just decided it. I just decided that I want my aspect ratio to be 10, and I already decided that my wing area was 193 meters squared. Now we can solve for b squared. B squared equals the square root of these two numbers. That's a multiplication sign. That's not b squared. That's just b. So my wingspan now equals 1.39 meters. Let's go ahead and chuck this in here. So we've decided our aspect ratio to be 10. And we got B, which is wingspan. Look at me not following, not being consistent. Whatever. My wingspan is 1.39 meters. So if you recall, my aspect ratio was a decision, and this was a calculated parameter, right? So sometimes you get to decide, sometimes it's given to you. Yeah, so now we have an aspect ratio. Guess we should also get our chord length. Now, again, this chord length is if your plane's wing is a rectangle. So this will give you a general chord length, but I would highly recommend not just having a rectangular wing. In almost any scenario, have some sort of taper, have some sort of more intricate wing plan form. However, for now, we're going to assume a rectangle. This is initial sizing after all. So we're going to use chord equals span over aspect ratio. So let's go ahead and do that. Can I have an empty piece on my paper? Right there. Chord equals span over aspect ratio. Why did I decide to lowercase this? Who knows? Sorry about that. Anyways, where were we? Chord, span, aspect ratio. Right. I am now calculating for the chord. This is a calculated parameter. So I can just put in my span 1.39 meters, or my aspect ratio, which I chose to be 10. Hopefully I don't need a calculator for this. I just move this over a decimal point, 1.39 meters. This is my chord. Again, if my plane was a rectangle, don't make your planes rectangles, guys. Chord equals 139 meters. So this is a relatively small chord, and that will help me keep my induced drag down on my glider. So let's get back to it. Tail sizing. So let's imagine our wing, right? This is kind of obvious, but if we look at our wing from above, we went ahead and got our wing area, we got our wing span, right? We got B, we got S, and we got C, which is our chord. So we have everything decided. I'm not going to go into this too much right now. If you choose to do a taper, your wing might actually end up looking like this, and that chord won't exactly be accurate. You're going to have a tip chord, you're going to have a mean aerodynamic chord, and you're going to have a root chord. We won't talk about that right now, but now we know our wing is fully initially sized. Now let's talk about tail sizing. Now, tail volume coefficient. Before we understand tail volume coefficient, let's go ahead and understand something else, actually. Let's imagine our plane. And I think I might have talked about this in one of the earlier videos. I made those earlier videos way before. It's been a minute, so I'm not sure what's in there. But what happens when what your wings really do is they create a force that goes up. The weight of your aircraft, your CG, makes it come down, and then your tail is a force that balances these two things. Whenever you're pitching up, it balances it, so it brings the force down, right? So what happens here is that this acts like a first-class lever. This is your lever arm, right? And we call this a tail lever arm. So what we know about levers is that if you have, say this is 2 feet and this is 1 pound, it's the same effect if it was 4 feet and this was 0.5 pounds, right? So whenever you pick your tail volume coefficient, you can have various tail lever arms and various tail areas, sorry, and they should relatively have the same effect if the tail volume coefficient is the same. Now, does that mean you should, make whatever tail lever arm you want? No, obviously there is impacts. You have an aircraft and let's say the tail is really close, then you're gonna have a lot of downwash and you don't want that. If you make it really long, you're gonna avoid that downwash and Your wing area is really small. Yay. Maybe you're going for an aircraft that has a lot of speed, and you want a smaller tail area. Maybe I'd recommend that. But then what's going to happen? You're going to have to make it very structurally sound because you made your aircraft longer for some reason, right? So go ahead and pick a reasonable tail volume coefficient and pick whatever lever arm you want and be confident that your tail area is going to suffice because you chose a good tail volume coefficient. That was a big rant. Let's go ahead and pick our tail volume coefficient now, shall we? So we have our horizontal tail volume coefficient and our vertical tail volume coefficient. We got a lot of numbers here, and this is just a decision parameter, right? So I'm going to go ahead and pick a nice big number for my horizontal. Let's start with horizontal. That's usually a thing. I'm going to pick 0.8, right? I'm going to go on the high end here, make sure I have a very nice and stable aircraft. Not necessarily how that works, but that's what my tail volume coefficient is going to be. So let's go ahead and write it with the rest of my parameters. Tail volume coefficient equals, maybe I should put horizontal, equals 0.08. Oops, just 0.8, isn't it? The vertical tail will probably have something different. All right, now let's go back. We do I have the formula here? No, I don't. Okay. So the tail volume coefficient formula looks like this. Tail volume coefficient, horizontal equals LHT for the lever arm times then the wing area of the tail area, I guess, right? Tail area, and over the chord of the wing, and then the wing area. So if you noticed, we've decided this as a decision parameter. We solved for this earlier, we solved for this earlier, and we're kind of looking for this right now. Now your lever arm can be whatever you want it to be, because our tail volume coefficient will force the area to compensate. Now, let's say you're going, for some reason, like you're going really fast and you want your tail area to be as low as possible. Your tail lever arm could also be calculated for. Typically, it's the lever arm that's a decision. So go ahead and pick whatever tail lever arm you want. However, I would recommend staying between, let's say this is your plane, and this is the chord of your aircraft. I would stay between 1 to 3 chord lengths away. So your tail lever arm should equal like your wing chord times 1 or times 3 or times 2.5 or whatever it is. So you can pick whatever tail lever arm you want. If you're making a commercial airplane, right, then you want to seat more people, you probably have a longer tail lever arm. Tail lever arms are usually given by the nature of, your aircraft. So the tail lever I'm going to pick, or you know what? I'm not going to pick a tail lever arm. I'm going to pick a multiplier. I'm going to pick 2.5, I think. You know what? I'm making a glider. Let's make it nice and long. Let's go 3. So I have 3 as my tail lever arm. That means I finally have all my parameters. I can go ahead and solve for my horizontal tail area. SHT. Let's see, what am I going to do? I'm going to move everything to the numerator except this. All right. I am not going to plug in all my numbers. I'm just going to My answer, let's see, what is that? Horizontal tail area equals 0.051. Sure. And for reference, my tail lever arm horizontal is equal to 0.41 meters, which is just, again, 3 times my chord. And my tail area is now compensating for it. So let's go ahead and, I'm not even going to write it at the top. I'm too lazy. Too lazy. We can also go ahead and decide an aspect ratio for the tail, like AR horizontal, I guess. Is that how you could write it? Horizontal. It's kind of just vibes, low key. I'll pick 3. If 3 is my horizontal, I'm going to use the same formula that we used earlier. This chord equals span over area. That means my H tail chord is equal to 0.12 meters. So we've got all of our horizontal tail parameters settled. So in terms of decision parameters, we had this one and this one. In terms of solved parameters, we had the H-tail chord that we solved for and the wing area that we solved for. So here's how these two things can play with each other. And of course, just follow this formula. Actually, I didn't show you guys the formula. It's this right here. I don't know why I've labeled this slide tail lever arm. These are the formulas for the tail volume coefficient. On the left is the horizontal tail volume. On the right is the vertical tail volume. Let's go ahead and solve for the vertical tail volume coefficient. Actually, you know what? Let's go back to our graph real quick. Oh, yes. What I would also like to mention is that tail lever arm isn't just the rear of your tail to the front of the rear of your wing to the front of your tail. It is actually, let's look at our plane from above. This will make it easier. There's our wing, there's our horizontal tail. 1/4 of the chord and 1/8 of the tail. So a quarter chord in and an eighth chord in here. This is actually your tail lever arm distance. So that makes, catting and stuff kind of annoying sometimes. But that is what that distance is. So let's keep that in mind as well. Let's choose a vertical tail volume coefficient. 0.06 sounds suitable. We'll do 0.06. Yeah. Let's go ahead and solve for it. I had to look at the formula because I'm cooked, it seems. So the coefficient times the lever arm times the V-tail area. Then it's the wingspan of our wingspan and our wing area. We have this, we have this, we have this. Let's go ahead and keep the lever arm the same. We are looking for our tail area. In that case, SVT equals CVT times wingspan times wing area all over the lever arm. We're going to keep the lever arm the same, by the way. And this comes out to, don't feel like plugging in the numbers. Area of vertical tail, 0.038 meters squared. Doesn't look unreasonable to me. Now we are done with our wing area. Let's choose an aspect ratio. I'm just going to go ahead and choose 1.5. What does that make our chord for our vertical tail? 0.16 meters. Am I missing anything? No, and we also have the lever arm from before. Perfect. Now let's go back and see if we have anything else left to solve for. Nope, we just have the dihedral, taper ratio, twist, and quite a few other things that I'd like to cover in the next video. Before I make the next video, I might make a intermediate video going over some basic math stuff. I feel like some things in the video can be confusing at times. And there's definitely other things I have to work on. Just let me know what I missed, what I can do better. That's what I'm all about. Um, yeah, and of course, contact me if there's any confusions.